In this lecture, we're going to talk about kinds of structures. Now, there are three basic kinds: folds, faults, and joints. This time we're going to talk, in this lecture will be folds. We'll talk about the plastic deformation in this particular lecture, and in the next one what we're going to talk about is the brittle, namely the faults and the joints. But before I get into that, I want to talk a little bit about modeling. Now, a lot of us have done modeling. As a kid, I built model airplanes, for example, and this is a good example of what modeling is all about. Consider making a model airplane. What you're going to do is to make a small reproduction of something that's much, much larger, you see? So you're reducing the size. Now, you don't just reduce the size, you also have to reduce the strength of the materials that you're going to be using. Everything has to be downsized, if you will. So think about the aircraft now, made of aluminum. What do you make this model out of? Well, you make it out of a combination of balsa wood and tissue paper. Okay, so we've downsized the material strength, you see. Well, that's not all. I mean, you look over that aircraft, it's got these big engines on it. Well, we have to downsize the energy from the engine system. So what did I downsize it to when I was a kid? To rubber bands. But here you have a model. It's reduced in size. It's reduced in material strengths. It's reduced in this case, energy source. But it does the same thing the big guy did. It still flies. So it's very important, you see, to do modeling like that. Well, in geology, we do modeling, and the idea is, if you look out in nature, there are things out there, mountain building perhaps, or whatever, you'd like to be able to sort of recreate what was going on somehow in the laboratory, if you will, because you see the end products out there. You see the end products of folds and faults and stuff. But you want to know, how did they get that way? Well, that's really what modeling's all about. For example, we already talked about one model. We were talking about streams, and I mentioned to you, for example, that we have in the business the thing called a flume. What it was, it's sort of a racetrack, and we run water around it. That's sort of a model now of a stream. The one I built, for example, was about 30 feet long and about 15 feet wide. The individual stream itself was about 2 feet wide, and as I remember, 1.5 feet deep. So obviously it's a reduction in size. And also in shape, because I don't know too many streams that run in a circle like that. But the idea was, what we wanted to do was to learn something about what happens at the base of the stream, what happens in the channel. Pretty tough to go out there into an actual stream and get down there in the channel seeing what's being picked up and what's being moved, especially if the stream is either highly turbulent or if it's just murky with sediment. So anyway, we build a model. So that would have been an example. Well, the results of that. Well, for example, we talked about that little chart that we had plotted with velocity versus turbulence and particle size across the bottom. Now, the data that generated that plot came from experiments done with flumes like this. Now, it wasn't my data, but it was somebody else's. But the idea was, remember, the things we learned. Well, the things we learned were, remember there was a point at which the up arrow and down arrow were equal to each other. In other words, the force of turbulence was equal to the force of gravity. At that point, or just beyond it, the particle should have been picked off the bottom and moved, and wasn't. See, we learned that from flume experiments. We found out that you actually have to add a little bit more energy beyond which is theoretically required to get the thing off the bottom and move. So that's why we learned that. And we learned that was true for, say, pebbles and granules and sand. But how about those really fine jobs down there? How about the clay and the silt? We had to come up with some idea. The flume experiments were saying, you can't run this thing fast enough to get those things off by themselves. So there was a theory that had to be evolved. What was it? Well, that's where they came up with this whole idea of the laminar flow. The laminar flow, the idea of that laminar layer, that was the result of flume experiments like these. When it was finally decided, the reason why those fine particles were so difficult to get off the bottom, the reason why you had to have the amount of energy needed for a pebble or a granule just to get those things off the bottom was because they totally were residing in this very, very thin layer called the laminar layer. Now, it's a theory. No one's ever seen the laminar layer, and no one ever will see the laminar layer. But note what a theory is. It's a scientifically sound idea, and I think that is, that explains what you see. And that's what we saw. It took so much energy to get those fine particles off the ground. Well, in a way, that would be an example of a model. And a lot of information that we understand now about how streams do their thing is gotten from very simple models like that. Well, another question then. Well, how about these structures we're talking about? Can we model some of these structures? Well, we're going to talk about folds, for example. All right, let's talk about modeling a fold. Here's all you have to do, and we do this in, for example, in the Geology 1 lab with the students, to give them some kind of a feeling for how folds form. So here would be a very, very simple model. You simply take a piece of paper on a table, and here's all you do with it. You push the edges together like that. Note, you have a fold. We'll name it a little bit later, but you have a fold. What can you tell? What should the student see? Well, note the student should see that we're talking about compressive forces here. You can't form a fold with tensional forces. Just try it with a piece of paper, pull it apart. It's impossible. So right off the bat, the student should see that we're talking here about compressive forces, and note, non-rotational compressive forces in this case, non-rotational compression. And here's something else they should see. Note the length of the fold. The fold is perpendicular. The trend of the fold is perpendicular to the forces. Well, do you see that out there in nature? Yeah, sure, you go out in nature and you see folds out there. And what you see are long linear folds. And how do we interpret them? Well, if they're symmetrical in cross-section like that one was, we interpret it being that it was a non-rotational compressive force, and the forces came perpendicular to the trend of the fold. And, this is something that happened 250 million years ago, but we can interpret what it was like back then just from the shape and the orientation of the fold. So that would be a good model. But note, in this little experiment, this was just, let's say, one layer of rock. Well, how about if you wanted to model, let's say, a number of layers of sedimentary rock stacked on top of each other? Could you do it with paper like that? Well, yeah, you know what I would do? I would take a ream of paper. You put a ream of paper down now and just push the edge of the ream together. The same thing will happen. It will form into that symmetrical fold that we just saw. The fold trend will be perpendicular to the compressive forces. But here's something else you'll note. If you watch very closely, what you'll see as those pieces of paper bend and move, they'll sort of move across each other like that. There's actually motion between each piece of paper and the one above and below. Question is, does that happening out there in nature? Well, let's go out and see. Well, if you went out to a fold, and this is especially true of shales, now that's why we look at them, because shales are very soft, and this is very prevalent among shales. So let's say you had two shale now layers. As it folds, you see they sort of move on each other like that. Well, if you look at the surface of those shale layers, they're going to be formed little sort of striations or grooves. We call them slickensides. And the orientation of them, note the orientation is always sort of parallel to the direction the rocks were moving against each other, not perpendicular, you see? So here these striations are going to be basically parallel to the applied forces. So what you see in the lab, actually you can see out in the field. That's what modeling is all about. Well, paper's one thing, but for example, could I say model faulting with a piece of paper or a ream of paper? No, so you have to go to some other material. So what we went to, and the one everybody used, was modeling clay. Well, it was a special kind of modeling clay. Actually, you had to make your own. What we found was best is there's a particular clay called kaolinite, which you don't have to worry about. But kaolinite clay, we mixed it with water, and we mixed it to make a certain consistency to it. And then what we would do, we had a table. It was called a clay cake table because we had a clay cake, you see. And we put this clay cake on the table, and one part of the table had a barrier we put one edge of the clay cake up against, and the other had a barrier that could be moved. So again, all we did was take this clay cake. This barrier could be moved either by hand or by a screw of some kind or by motor, and the idea is you can do exactly the same thing with the clay cake as you did with the paper. Now here's an important point. Depending upon what you want to do, let's say we wanted to do a fold. Remember, fold is plastic deformation. So what we did, we mixed a clay that was very, well, back in like making a dough, very thin, you see. We wanted it to hold its shape, but we wanted it to be able to flow, because that's what folds are. So we make up a special kind of clay with quite a bit of water in it, more water than normal. And what happens when you compress that? The same kind of folds will form we did with a piece of paper, except now it's a little bit more realistic. We can put, if we want to have layers, you can do that. You put a layer of clay down, make another, roll out a layer, put stack layers on top of each other. Note if we wanted to say, model a fault, we want to break this thing now. Well, you see that the consistency of that kind of clay is too fluid. It'll bend, it's plastic deformation, but now we want it to break. Well, what we would do would be to take another kind of batch of clay, would add more clay minerals in with it. It would get a little stiffer now than before. So now when we compress it, rather than flowing, it would break. So you see that the kind of stuff you pick basically is depending upon what you're trying to model. Well, the bottom line is that there was an awful lot of work done with these clay models, and I was involved in that years ago. And we got an awful lot of information about what went on in mountain building. Like I say, what you see in a mountain range, the Appalachians, the Himalayas, I don't care which one it is, you see the end product of the deformational history. What I want to know is, can I explain what I see out there that's the end product? How did it get that way? Well, a lot of our information was gotten by these models. Now, there are a lot of people who are anti-model. The reason why, whenever you scale down, you see we're scaling down size. One of the problems they used to say, well, you're not really scaling down the strength of material because that clay is too strong. If you really scaled it down, everything down for, let's say, to that size, you're going to have to use something a lot weaker in strength than clay. And see, that was their argument. A lot of people try. They use, for example, Jello. Even I tried that one. It didn't work very well. But anyway, so there are a lot of people who wouldn't accept it. But on the other hand, there were those of us who said, well, I understand the shortcomings of this, but we got information that seemed to be duplicating what's out there in nature, and that's all we wanted to do anyway. So anyway, this whole idea of modeling was a big thing. We don't do much in the way of clay modeling anymore, but we still model. How? Computer modeling. Computer modeling is a big, big thing nowadays. All you need is someone who's really smart enough to write some kind of a mathematical relationship, you see, to describe whatever it is you're going to do, and then someone who's sharp enough to write the program to do it. But we're always modeling things now, and you've seen all kinds of computer modeling. For example, here's what we're modeling a lot of. Right now, a big emphasis on modeling is, let's say, the core. We're modeling the core of Earth. Why? Well, we know it's molten. The seismologist told us that a long time ago. But here's some things we don't quite understand. For example, where does this magnetic field come from? Well, back when I took geology first, and throughout my career, I used to simply tell students, it's as it rotates, as the solid part, the mantle rotates around this liquid core, there's a dynamo effect. What's dynamo effect? Well, I'm not really sure what that means. See, we don't understand even today where this magnetic field came from. So they're trying to model now what really does go on within this liquid core that would possibly generate a magnetic field like that. And here's the other thing we really don't still understand. Why does it flip? We talked about those magnetic reversals. Well, there are times when the magnetic field of the Earth switches. North Pole becomes South Pole becomes North Pole. And the important thing is, this doesn't happen really slowly over a period of several million years. This happens like geologically right now. Now it's switched. Now it's switched back. Now it's switched. Why? What's causing that reversal? I don't think anybody knows that answer. The answer may lie in those modeling experiments they're doing on the core and the mantle. So there's an awful lot of work still going on in modeling. It's just that we're using different tools now than we did before. Okay, so much for modeling. Let's go on to a discussion now of folds. Folds all form from compression. That's point number one. You cannot form a fold, for example, with a piece of paper, try to pull it up. You're not going to do any folding, pulling it out under tension. So they're all formed as a result of compression. And there's basically three different kinds of folds. The monocline, the anticline, and the syncline. Now, monocline, mono means one. A monocline is basically a single sloping curve like that. A fold that simply has one side to it, if you will. Where do you see these? Very commonly, they develop where you have some kind of a major uplift. Now, we've talked an awful lot, for example, about the forces that lifted the Colorado Plateau 10 billion years ago to where it is now. Well, when it lifted it up, remember, inside the Colorado Plateau, there was no deformation at all, so to speak of. Where the deformation is along the outside edge. If you go around the outside edge of the Colorado Plateau, what you'll see are sedimentary rocks sort of just draped down over the edge, forming monoclinal folds. So that would be an example of a monocline. The two big ones, however, are anticlines an up warp, and a syncline, which is a down warp. Now, you can have an anticline all by itself, or I guess you could have a syncline all by itself. I've never seen one like that. Wherever they form under compression, you have them in sets. Anticline, syncline, like that. Now, here's a question students always ask. Where's the anticline start and end? Well, I guess you could say the anticline starts at the bottom of the syncline to the bottom of the next syncline. Well, how about the syncline? Well, it starts at the top of the anticline to the top of the next anticline. But that's not how we do it. We simply say the anticline is the up warp in the Earth's crust, the syncline is the down warp in the Earth's crust. So anyway, those are the three basic kinds. Now, what I'd like to do is talk a little bit about some of the basic parameters we use to describe these things. Let's take, for example, amplitude. Remember when I did that little experiment about pushing the paper together, it sort of bowed up like that, made a symmetrical fold? Well, the height of that, the height from the top of the fold to the bottom of the fold, basically that's the amplitude. And it's simply measured in feet. What's the significance of it? Well, just think about this. If we took that piece of paper and did the experiment again, and again in lab I used to have my students do this, at first, as you start pushing together, the first amplitude obviously has to start out small, and as you continue to push, the amplitude grows greater and greater and greater. In other words, the fold increases in amplitude. Significance, what is it telling you? Well, what it's really saying is the longer you apply the force, or perhaps the greater force you apply, the greater the amplitude is going to be. So if you go out in nature and you look at a series of folds, and the amplitude is changing within this area, you can use the amplitude the amplitude of the fold to tell which of those was being worked on the longest or with the most intense energy, and which had the least. So you see, that's a pretty important thing, the amplitude. So we pay a lot of attention to the amplitude. The next one is a thing called the axial plane. Now, what the axial plane is, it's an imaginary plane that attempts to divide the fold along its length into two equal halves. And we'll see the significance of the axial plane whenever we start talking about different kinds of folds. But that's basically what it is. It's just an imaginary plane that is drawn parallel to the length of the fold, which divides it into equal halves. Another thing are the limbs. We talk about the limbs of the fold. Well, the limbs of the fold are simply the rocks that come off the axis of the anticline or go toward the axis of the syncline. So that's what the limbs are. Now, one of the things we have to describe on the limbs, however, is their attitude in three-dimensional space. So we have a measurement we call strike and dip. Now, this is pretty important because there are all kinds of planar features out there. The limbs of a fold, of course, is a planar feature. A fault surface is a planar feature. A layer of rock is a planar feature. So if you want to describe this particular plane, let's say, to someone else and have them picture it clearly in their minds, what you do is you measure what we call strike and dip. So here's what it is. First of all, the strike. The strike is the intersection between the plane and the horizontal. Note that's a line, and the line has a direction. So you determine the direction of that line. And we determine directions of things relative to the North Pole. And so we say that line is striking north, or it's north 45 east, or it's north 45 west, whatever the strike is. So as soon as you tell a listener that, all of a sudden they know now which direction the strike is. They can picture this in their mind. So here we have this plane, and obviously there's a dip to it. Well, the dip is simply the angle between the horizontal and the plane. So you tell the listener again, the plane is striking, let's say, due north, and it's dipping 45 degrees. Okay, I can visualize that, but there's two possibilities. If this is the strike, the plane could be dipping in that direction, that limb, or it could be on the other side. How do I know which one of these limbs we're talking about? Well, the way you do that is whenever you give the dip, you tell which direction it's dipping. For example, let's say, for simplicity purpose, let's say the strike is due north. And here's one plane. That's dipping to the east. Here's the other one dipping to the west. So if I told this person, this plane has a strike of north-south, dips 45 degrees to the east, always perpendicular, I don't care where this person is in the world, they can picture that plane in three-dimensional space. And that's what the importance of strike and dip's all about. Now the last one, we're talking about this thing called plunge. these folds, we made that little fold with a piece of paper. It looked like it was going to go on forever, but of course folds can't go on forever. So what they end up doing, they end by doing what we call plunging. Now here's what plunging is. What I would do, I would take that piece of paper again, and I'll hold the piece of paper down with, say, the backs of your hands and your thumbs, and with your fingers now, just push those edges together, and you'll see what happens is they'll form a fold. Note, you can see the fold on one end, the end away from me, but note, back here next to me, there is no fold. In other words, it's dying out, it's coming to an end, it's plunging. That's how folds come to an end. They come to an end by plunging. And so what we do, we measure the axis of the fold direction and the angle between the axis, which would be the intersection of the limbs with each other, and the horizontal. So in other words, that's how all folds come to an end. So anyway, that would be plunge. So those are the descriptions we make of all the folds, and if you do that, pretty soon you have a pretty good idea of not only the forces that created this fold, but which direction they came from and how long the forces acted along the fold. Okay, so much for the parameters. Now, let's finally get around to the different kinds. Let's say we take, for example, the simplest possibility. We're going to take now and picture applying non-rotational compression. Non-rotational compression. And picture now, as you do that, what's going to happen, the little experiment we did, the very first one, you're going to form a fold, and the description of the fold now, it's going to say axial plane is vertical. Okay? Limbs dip away from the axial plane in opposite directions at equal angles. The cross section is symmetrical, so that would be a symmetrical fold. Significance: if you go out and if you see a symmetrical fold, the picture a geologist would have in their minds, this fold formed, undoubtedly, probably at least, from non-rotational compression, and as a result, it formed simply a symmetrical fold. So that's what symmetrical folds tell us, simply non-rotational compression. Now let me change the scenario a little bit here. Let's say instead of directly non-rotational compression, which would be like if you took your hands and palm down and just put your fingers together side by side like that, that would be the non-rotational compression. Now what we're going to do, picture taking your hands and having one above the other, maybe just a little bit, not a lot. But now you see if you moved your hands together, one would sort of pass over top of the one below. That would be rotational compression now. So here's what we're going to do. We're going to have a scenario where we're going to take our block and we're going to compress it again, but this time under rotational compression. So back to the block on our clay table. As we start this experiment, the first fold that undoubtedly will form, always does seem to form, at least in my experience, the first fold will be symmetrical. And it may actually increase in amplitude some, but very, very soon what's going to happen? Picture now, let's say your right hand moving over top of your left hand. What's going to happen is the fold is going to start changing shape. What's going to happen as you continue to apply the force, the axial plane now is going to start tilting over in the direction of your right hand moving across your left. And as the axial plane tips over, what's going to happen to the limbs of the fold, now they're dipping away from the axis all right, but note, different directions, but different angles. One steeper than the other, and the steeper one will always be the one that's dipping in the direction in which your right hand is moving over top of your left. And if you continue to do that, the sequence is as follows. The asymmetry now of the fold simply starts to change. As we go on and apply more force to it and more energy to it, the axial plane continues to tip over on its side like that. And pretty soon you're going to get to the point now where you have these folds that are asymmetric, are going to get to the point where that far limb, the one that's pointing in the direction in which your right hand was moving, that one is now vertical. It's still asymmetric, but then the next point is it's going to go beyond that point, and now we have the scenario where we have an inclined axial plane, both limbs dipping in the same direction. Now you see it's beyond asymmetry now, it's overturned. And if you continue to go beyond that, what you're going to end up with ultimately is that the axial plane and the limbs are going to, as they say, approach the horizontal. We call that recumbent folds. So note the sequence of events. You start off with symmetrical folds, then you go to asymmetric folds, then you go to overturned folds, and the ultimate in deformation, folding deformation, is recumbency. Well, can I give you a really good example of that? Well, yes, I can. And what I'd like you to think about now is a cross-section of the Appalachians. Now, I use the Appalachians simply because I'm more familiar with it than any other mountain range, but this could apply to any of the major mountain ranges of the world. The Appalachians, the Alps, the Himalaya, it makes no difference. So here's the picture. If you look at the cross-section of the Appalachians, what we do is we break it into what we call physiographic provinces. Now, the physiographic provinces, that's an area that has common rock types, structures, history, and topography. And so if we look at the Appalachians, what you're going to see from the east coast to the west, as you come off the coastal plain, the first of the provinces you run into is going to be what we call the Piedmont. Let me just tell you what the provinces are first. Now, this will be east to west. You have the Piedmont, then you run into the Blue Ridge province, and then you run into what we call the Great Valley, which is known locally as the Shenandoah or whatever. And then the next one is the Appalachian Mountains themselves. We call that the Valley and Ridge province. Here's where you have those long parallel ridges and long parallel valleys. And then the next one in line to the west, you get into the plateau, and then the next one is what I call the high plateau. And then finally you have what we call the low plateau. The western edge of the low plateau probably is somewhere around, if you put a line down through westernmost West Virginia, easternmost Ohio, and on down through Kentucky, that probably would be the western edge of the Appalachians. Now let's go back and look at the folds. Just the folds now. We'll ignore the faults at the moment because we're going to see the faults later. If you go to the Piedmont, first thing you're going to find is you can't find any rocks in the Piedmont. These are highly deformed metamorphic rocks. They weather very, very fast, and as a result are covered with regolith and soil. But if you can get to a quarry, and there are some, and look at it, here's what you're going to see. Highly deformed metamorphic rocks. You're going to find volcanic rocks in there. But in terms of the folds, highly, highly recumbent folding. I mean, it just looks like a marble cake kind of thing. Just picture that. When you come over then to the Blue Ridge, what you see as you cross the Blue Ridge, you see not recumbent folds, but overturned folds, pretty highly overturned folds in the Blue Ridge. In other words, not quite the extent of deformation. Once you get into the Great Valley, now here's another place, a little hard to find outcrops because it's a limestone valley, and the limestone weathers very fast and covers with soil. But again, if you go to quarries, here's what you're going to see. You're going to see overturned folds again, but not with the degree of overturning in the Blue Ridge. Then when you get over to the Valley and Ridge, the real mountains, these are the ones you can really see as you drive through on the interstate, for example. What you're going to see are the folds are highly, highly asymmetric. Usually that western limb is almost vertical in almost all the cases, so they're highly asymmetric now. Once you get up onto the plateau, things change a lot. Once you get up on the plateau, this would be now what I would call the high plateau. The folds are symmetrical. Okay, but high amplitude. The high amplitude, high enough, for example, that they can actually appear on the surface as ridge lines. So if you go with the high plateau, you're looking at long parallel ridges and long parallel valleys, nowhere near the magnitude of the valley and ridge, but they're there because of these symmetrical folds. Now, once you go west of that, now you're into the low plateau. Morgantown, for example, is right at the very eastern edge of the low plateau. In the low plateau now, you do have folds. They are symmetrical folds, but the amplitudes are very, very small. Very, very small amplitudes. They're so small, for example, they do not hold up any ridge lines at all. If you drive from Morgantown west, what the area looks like just gently rolling hills, but no kind of structural control do you see at the surface. Now, these rocks, as you're driving along, the rocks basically look like they're horizontal. Why? Because we're talking about symmetrical anticlines and synclines with the limbs with the dips of like 2 degrees, maybe 3. Now, the significance of 2 to 3, your eye and mine cannot perceive that as sloping. To your eye and mine, a 2 or 3 degree slope would basically be a horizontal surface. So as you drive through this low plateau, this westernmost edge, that's what you're going to see, basically horizontal rocks. Now, what does that tell us about the Appalachians? That tells us that the energy came from east to west. It says the greatest amount of energy involved in the formation of the Appalachians was over there in that easternmost province in the Piedmont, and as you come to the west, the amount of energy is decreasing all the time. Now, they've noticed that for 150 years. But why? They never understood that. What was it about the creation of the Appalachians that results in this very systematic change in the fold attitudes as you go from east to west? They didn't know. Why? Plate tectonics hadn't come onto the scene yet. So here's another reason why plate tectonics came on top, why it gave us information we never had before. Now we understand how the Appalachian formed. How did it form? There was a big collision over there to the east, and that collision was a collision between two continental masses that resulted in the formation of Pangaea. And now we're back to Pangaea again. Well, we'll come back to this little structure of Appalachia, because the other thing we want to talk about are, in fact, the faults.